Hello, welcome back to our office hour. Today we'll talk about the discrete wavelet transform. So this is a continuation, the last lecture we have on wavelets. The discrete wavelet transform is different from the others, in part because it's really industrial strength wavelet transformation. And it's a technology enabling computing. And as you'll see, when we get to do that, it tends to get a little more technical, maybe some more details, a little more abstract than the basic wavelet idea. So for today, I recommend you use this lecture maybe to listen to it first, just to make sure you get the basic ideas. Don't worry about the mathematics first. Then you can listen to it again, or then read the book, but it's good to get an overview. Once you get the overview, then you can see how the pieces fall together. Okay, so let's get on with it. Let's look at the first slide. So what we have here is a review. You know all this. This is just our wavelets in a nutshell. And if you remember last time, we looked at a number of wavelets, and here's this beautiful picture in multicolored grays of 3 wavelets. Okay? What are wavelets? Wavelets are just wave packets. Okay? It's just another word for it. It's a small wave, but what in physics we'll call a wave packet. We particularly like them, and we use them, and we need them in order to analyze non-stationary signals. So it's like Fourier analysis, except the signal changes with time. And it's not a periodic signal, and it has different waveforms at different times, so we need a different tool to get that. And the wavelets are just our basis functions. So we'll expand a signal in terms of variations of wavelets, like you have up here. Okay? And if you look at them, they're all similar in the extent that they oscillate. Other than that, they can have varied forms. That doesn't matter. Okay? What really does matter with wavelets, the heart of wavelets and the heart of what we do today, is that we can vary their scale and where they're located. And when we say scale, we mean like scale on a map. We can expand them or shrink them. And since they have a finite number of oscillations, when you expand them or shrink them, you change the frequency. So we'll have wavelets of one type of various frequencies, and we can move them here, there, every place, and translate them. That's what we vary. Okay? And as a consequence of just the basic mathematics of Fourier transforms, really, of wavelets, each wavelet which has a finite interval over time that it exists for, and it has a finite range of frequencies. They all oscillate, so you have a bunch of frequencies. So they have a width. They have a width delta t, or delta tau here, and a frequency range delta omega. And the uncertainty principle, as applied to wavelets, tells us that the product of the width and the product of the width in frequency is always greater than or equal to some number, 2 pi. And that's just like quantum mechanics. If we try to have a wavelet only at one time, very definite time, we need a broad range of frequencies. Okay? So let's go on. What's the discrete wavelet transform? Well, we have, if you want, our problem. And our problem is we have a signal, presumably a non-stationary signal, and we want you to determine n independent wavelet transforms, and we call them y, capital Y, sub I and j. I and j obviously indicating the scale and the location and time. Okay, but we just want you to determine n, where n is the number of measurements made. Or make n measurements and determine n independent ones. And to do this uniquely in the best possible way. Okay, so what do we have? This is our definition of the wavelet transform. And recall, it says this is the continuous transform. We have a transform. There's the scale parameter. There's the time parameter, or the time location. And we integrate over all time a wavelet of some scale and some time. It's a daughter wavelet, and the y of t is our signal. So that's our signal. We multiply the signal by a daughter wavelet, integrate over all time, and then we do this for all possible values of s and tau, and that gives us the whole transform. Now we want to say, okay, but we've only measured the signal at discrete times, n times. And then that means at best we can only determine n wavelets, wavelet transforms, and we want those wavelet transforms to be independent. And we don't want to do any more work than we have to. probably appreciate that. Okay? So we want to minimize the work done. We want this to be fast, but we want it to be as good as could be. What does that mean, as good as could be? Well, here's a hint. If it's lossless, that means we want to be able to exactly reproduce the input signal when we're done. Okay? We have the input signal has n measurements. We want to reproduce those n measurements exactly. And exactly means, well, consistent with the uncertainty principle, because you can't determine the signal better than what you've measured, and the basic mathematics limits you. So that's one hint. We want to be able to have lossless compression of data, as they say, or be able to re-invert the transform to a lossless signal. Fine. But we also want everything. We don't want too much. We want to have lossy compression as well. Say that, lossy compression. I don't know if it's really a word, it's used. And that means we want to be able to say, what if I lose some of the high resolution that was recorded originally, and I'm willing to put up with less resolution in order to have a smaller signal? And if all I want to do is, show the signal on my cell phone here or something, I don't need a big picture. Okay? So I want to be able to make a very small, tiny picture or a very big, beautiful picture. It's up to me. That's the problem. How do we solve it? Well, let's look at the next slide, number 17. Well, here's the question. How do you discretize a wavelet transformation? Well, the heart of wavelets is this variable scaling and this variable translation. And you want to have different scales all put together, stored, and different translations. How do you decide what they are? Well, one way which seems to work very well, particularly in nature, in practice, and it's probably related to the fractal nature of many of these objects, is to say, let's have our scale parameter, 1 over the frequency, be related to 2 to the power j. So we say index j goes from 0 to n minus 1, say, or whatever number. When we mean that the scale varies by a factor of 2 each time. It gets 2 larger and larger. Likewise, or inverse likewise, the time parameter tau goes like some constant k over 2 to the j. So as we vary the other index, the time index, we get that moving in uniform steps of whatever the scale was, but the scale has this didactic, as it's called, because the power of 2, didactic power. And these two, s and tau, of course, are related by the uncertainty principle, so when one gets bigger, the other gets smaller. That's all that says. So that's very cute. That's the grid. It's a didactic grid. It sounds philosophical, but it's not. And that's how we define the discrete wavelet transform. So the discrete wavelet transform is here. We have our mother wavelet, capital psi. We have some normalization factor, which, just in practice, it works out well, and some of the theorems then can be calculated. And we have here what we mean by our wavelet, discrete wavelets. J and k are the indices, so it's the mother at time t minus the time translation, k divided by, right there is the divided by, t minus k over 2j, and then with the scale parameter, 2j in the denominator as well. Okay, so that's the definition of the wavelet. And if we then do the transform, the wavelet transform, so here we have on equation 3, what we showed you on the previous, the wavelet transform. And what do we have? Well, we have two things going on. One, of course, is if we have an integral, we can only approximate the integral on the computer, and we do that with a finite sum. So there's our sum, and we sum over would-be weights. But here we're using the trapezoid rule, so we just do h, because we'll sum over just the points where the signal has been measured. So it's just like what we did with the transform, the discrete Fourier transform. So we're summing over the measurement values, which are here, and then we have these transform wavelet values as well. Okay, so that is what we evaluate, okay, numerically. But we hardly ever do that. Okay, we're more clever than that, and one of the clevernesses is by thinking, what ranges do we cover? So look now at the next slide, slide 21, and see if you can figure out what it's trying to tell you. Well, what this slide shows us is that the way we're supposed to sample, and the way this didactic grid will, sample a signal, where we measure the signal, is in the signal space. So we have frequency and time. We're measuring the signal at some time, and at each time we have to have different scales, which is what we call the frequency here. And it's such that at high frequency, high values of omega, or frequency, we need to have a larger range of back and forth here of frequencies that we measure. Now that makes sense. If you're at a high frequency, the signal is varying very quickly, you need to record lots of details. And if you want many details, you have to stay at one time and get all the wiggles. Okay, that's what this means. So, but if we go to low frequency, at the bottom here, where, for example, we have black, if it's very low frequency, it varies very slowly, then we can have a long time interval for those frequencies. So we can just have measurements over a wavelet that spreads over time, but if it's at low enough frequency. So the two go together. Regardless, at each time interval, say each little box here of some sort, we have to have different scales present. Okay? So the uncertainty principle, so now the mathematics, remember, the uncertainty principle tells us that for any wave packet, the frequency range times the time range is greater than 2 pi. Fine, we can use that to advantage by not being wasteful. That says, whenever we do a measurement, don't do any more than is needed. Make sure each of these boxes has the same area. So if they have the area 2 pi, that's the best we can do within the uncertainty principle. Cover that range with frequencies and times, and we're done. That's one of those things that's easy to say. How you do it in practice is, of course, where the genius is. Okay? And these methods are very clever, and when we're done, very simple and fast, but sort of ingenious and probably somewhat empirical. You don't have to see all this, but if you have some feel of where it should be, when you work it out, try it out, and it works, then you say, aha, I knew it all the time. Okay, so let's look at how this is done in practice. Slide 26. Well, slide 26 is showing you a filter tree. And we'll talk about this filter tree in detail on the next slide, but here it's sort of nice to just see what filters look like. And I spend these time making these illustrations. You may as well look at them for more than 10 seconds. What's a filter? Okay. Well, if you think of what a discrete wavelet transform is, those equations we just wrote down, they really are equivalent to a filter. What we think of in electronic shop is just, high filter or a low filter. Okay? What does a filter do? Well, if you think of what a filter does, you pass a signal through a filter. A signal contains various frequencies, and when you're done, you get an output which has a different range of frequencies. It emphasizes some, it decreases other. Well, in a sense, this is really equivalent to analyzing that signal at different scales, which is just another word for frequency. Okay? So if we have a filter, and like this tree here, and we pass a signal through it, we end up with output at different frequencies, different scales. That's really what a wavelet transform does as well. And that's why this is called an MRA. Oh, God, I have to remember. Oh, it says up there, multi-resolution analysis. Okay, it sounds very fancy, but it's analyzing the signal at different levels of resolution, which is just what we get out of filters. Okay, so what you see here is the basic steps, and we'll outline that in the next few slides in more and different kinds of details. What are we doing? We're sampling a signal, which means we're taking measurements of it. We're filtering it. We're passing it through filters. There'll be digital filters, means on a computer, numerical filters, and that rescales them or re-emphasizes some parts and de-emphasizes others. Then we'll sample it again to resolve the signal at yet other scales and have more and other information. Okay? So mathematically, we have two equations here. G of t is a definition of the filter. You have to think back, maybe another 3 or 4 lectures to remember that, and if your memory's good, good. If not, here it is. So we have a filter, and we start off with a signal, a y of t, and the output is g of t, and h of t is just the filter function, as we called it. Well, if we look at what a transform does, the transform starts off, again, here's our signal, y of t. We then multiply the signal by a filter function. Well, the filter function here is just the wavelet. Okay, the mother wavelet at some time and scale, and we get integrate over all time. So the two are equivalent. So then we see, okay, when we're done, we discretize the integral, so we're left with a sum over I. We have weights here, which correspond to the integration weights, and we have the values of y. So in practice, of course, what we have is that we may as well have, as part of the integration weights here, put together the values of the wavelets at these particular points. So we can combine into one number here, call it C or D, the filter coefficients, as they're called. So they're the combination of the weights from doing the integration and the actual values of the wavelet at those times. And then you say, how are you going to determine those? You just determine them empirically to get sort of the answer you want and a nice answer. But at least you know where it's coming from. We're not just making it up. So let's talk about this filtering. Look at the next slide, 31, please. Okay. So now we see here on this slide, we see boxes. We see boxes with H's, L's, and these little arrows with 2's. Okay. What does that mean? Well, obvious. H is a high-pass filter. High-pass filter lets through the high frequencies, which is what the details are in. The little wiggles, a little bit of hair here and there, on face, say. The low frequency, L, is a low frequency. It lets through the low frequencies. Each filter lowers the scale. Each filtering process lowers the scale, so we keep looking as we move from left to right at lower and lower scale. Okay, smaller and more details we're getting out. The little arrow, down arrow with a 2, is factor of 2 decimation, as it's called. In other words, decimation means you kill off every 10th soldier like the Romans used to do, but we're not cruel like they were. Okay, so we only do factor of 2 killing, so we only remove half of the signal at each time, which is maybe more than a 10th. But anyway, so it takes half the signal away, just throws it away because you have to obey the uncertainty principle. You don't want to save any more information than you possibly can use. You can save that information, you can use it to reconstruct the signal, but it doesn't buy you anything more, and that's the ingenious part of this. Okay? So this is also called subsampling, when you keep subtracting, removing samples, and then look at what's left and sample it again. And it's a process which, if you repeat it, keeps the areas in that diagram and frequency time space, keeps those areas of the sampling constant. You have to do some analysis to really convince yourself of that. But by doing that, that's the best we can do. So it's an optimization. Okay? So let's take a break here, look at this beautiful picture, and we'll talk about this a drop more. Okay. So we have a textbook here that, of course, you've all gone out and bought. And if you read about the process, both in the textbook chapter and in the appendix, we go through the details of an actual JPEG storage and what this means. So here you can see very quickly from the textbook the beautiful daughter of one of my co-author's colleagues. And here it's stored with all the details. Here it's stored by throwing out some of the more detailed components. And if you look closer, you can see, oh, over here you can see some noise coming in where there were little bright highlights before. And then if you have even lower resolution, you can see the graininess, and you can see even more noise coming in. But, so this is what you do all the time when you play with pictures. So here we have a picture I just happened to find someplace of a fisherman, I think, and it's a digital picture. And you can look at it, you can enlarge it, no problem, so it gets bigger and bigger. You can see, it's sort of impressive, because if you keep enlarging it, you still see more and more details. And who do you want to look at? The fish is probably better to look at than this ugly guy. Okay. Unless you're animals' rights types, and then you probably prefer the guy. But as you keep looking, I'll go back to the ugly guy, because you can see there's a lot of details there, which you didn't see at first. But we can take this picture, and edit it, and we can resample it. Okay, so here we can say, let's sample it at, rather than 100%, that's all the information that I took with my expensive camera. If we just sample it at 10%, it throws away 90% of the signal. Okay, so let's say here, 10%, okay, and what you get here is, oh, there's the picture again. So this has thrown away 90% of what's there, but it still looks fine. Why is that? Well, because it's thrown away a lot of the details. The gross features are still there, and some of the details. And at this small a size, you can't see the details. If we start enlarging this baby, what we see is, oh, the details aren't there. Fortunately, his face gets more and more grainy and less able to see each time we enlarge it. And then, it got tired of enlarging it. So, Control L. So, that's an example of this feature I showed you here. Let's try to get us back to life now. Okay. So, that's an example of the various resolutions and how fast it was for the computer just to throw them away and reconstitute the picture. So that's a JPEG 2 storage based on these wavelets, and it's essentially instantaneous to decompose, instantaneous to reinvert the transform. That's why these techniques are used. So let's summarize now before we'll give you another little lecture on some of the technical details. What we've shown you is this sort of pyramid discrete wavelet transform algorithm, where you start off with a signal and we consecutively compress the data by putting it through high and low pass filters and throwing out until we're all done. But when we're all done, we have a separate bunch of coefficients for high resolution, another bunch of coefficients for lower resolution. The lower resolution gives you the shape. And if we want to throw away some high resolution, make the picture a little smaller, fine. That compresses the data. That's why, you can get lots of little devices with small pictures. They don't take up much memory. The smooth information is in the low frequency stuff, the large S components, detailed in the small S, the high frequency. That makes sense. And we've said all that, okay? We've said this is how we lower the data resolution, and we've seen how it's rapid. Okay, so we've given you an example of that. So now let's go on. Take a break if you want. Now's a good time. And let's talk about that actual algorithm and how it's implemented. Okay, so did you take a little break? I did. So this is our summary. Let's go on and talk about the actual digital filtering process. Fascinating, but rather surprisingly sophisticated. So here's slide 44. This is the pyramid algorithm described graphically. And I advise you, let's talk about this a little bit here, but you probably need to read the text to understand each piece and see how the pieces fit together. So what we have here is, we have lots of stuff on this graph. This is the pyramid. Notice how, start off with n signals, a finite number of signals. That's the input. We pass it through a high and a low pass filter. Fine. And what do? Well, the high pass filter is high resolution. That's why I like to say that. That's the high frequency stuff. Okay? We throw away half of it. Fine. But then we save immediately n over 2 d coefficients. D because they're detailed. Okay? We save that, period. Okay? So half of the signal we've saved right here because we need that to get the high details. All right. Then we take the low pass filter, which we pass the full sample through, fine. And then we get n over 2 of those coefficients as well through that. They're not the detailed ones. And that we get that after decimation, we get that as output. We now continue saving, passing that output from the low through other low and high pass filters. Each time we get the detailed coefficients, we always save them. Okay? And we save some of the smooth coefficients as well. But we're always saving more and more detailed coefficients, and we keep this process up until, as you see here, The first step we have capital N over 2, n can be a large number. The last step, we just get 2 coefficients out on details, 2 are smoother ones, and we save those. Okay? So that's how you end. You start off with some number, when you just have 2 left, it's just iterative. So it's very good on the computer, it just repeats, and this is very fast to do because these are just matrix multiplications. So as we see on the next slide, okay, slide 45, here's an example with n equals 8 data signals. So here on the left, we have our signal. So this is our input here. Okay? These are the measured 8 values. And first we filter it. And if we filter it, we then get an output which is a smooth, detailed, sort of mixed together. This is typical for one kind of filter we're using. The 1 here indicates that this is the first iteration in the filtering process. So these all have 1s on them. 2, 3, 4 correspond to the output from the data. And then we reorder them. We reorder them so we have the smooth on top. We have 4 smooth. Now we have 4 detailed. So now we can apply the same filter or some variation of that filter to those data, and we get, again, we get them mixed up, and then we reorder them, and now we have 2 smooth on top, 4 detail, and the rest detail. So we throw away all the other smooth. As I was saying, we save 2 smooth, but here we're saving 6 detailed because, well, we need more detailed information than you need smooth information. The general shape doesn't need a lot, but the little hairs on his face or those little dots on the fish needed lots of detail. Okay? How we do this, of course, on the computer is by matrix multiplication. So we have a series of an n-dimensional matrix, n being the number of data points, and we multiply our signal, small y, by that right here to get the output, which is the transform. So here is our signal. In the text, we go through one derivation for popular filter coefficients. That's what these C's are. And also for why these 4 coefficients are arranged in a matrix like this. So here it can handle more than just a small number of signals. It can be enlarged by just continuing the process. Okay? So we do the multiplication by the matrix. We end up with an output, just as we saw in the previous slide. We reorder, then multiply again and again, throwing away bits and pieces until finally we just have 2 smooth outputs remaining. So the point of this slide is right here. This is the filtering. The filtering is just a simple matrix multiplication by these coefficients. Okay? What if we wanted to get back to the original signal? Remember how quick it was on the computer? That's because all you do is you take the transform, which we have here on the right, multiply it by the inverse of this matrix. Now you might be thinking, gee, I remember I took linear algebra. It takes a long time to calculate the inverse. Well, yes, but these are very simple orthogonal matrices. The inverse is just the transpose, rows and columns. So you don't have to do any work really calculating the inverse. You just transpose the matrix or interchange I and j when you do a sum. So that's how we get back. So that's one reason when you saw the figures, the image coming back so quickly. Why was it so quick? Your little camera or the computer program is just doing this matrix multiplication. If you remember, I think that image I showed you had 2,000 roughly by 1,000 pixels or dots. So it had about 6 million elements there, but the multiplications are very quick. Okay, so here's an example. Look at slide 48, please. This is a graphical example of the analysis of a chirp signal. Now this is identical to what I've said on the last 2 slides. One I showed you how it was done by matrix multiplication, the other with a filter tree. Here is showing you the same thing. It's just showing you the output at each step of the process of the signal. So we start up here on the upper left with a green, that's our full chirp signal, sine of 60 t squared. So it has one frequency here and the frequency changes. We then have after low and high pass, we get two outputs here. And we're connecting the dots, because the output would just be numbers. And we're connecting it here so you can see that it looks like the signal. So we get high and low. And then we filter those again. We get more and more output. But now you can see it's spread out more and more. There's actually less information coming out. There are fewer numbers. So we started off with 512. We're down here. I can't tell you. But it's a smaller number. And then as we go down, you can see it's really just histograms left. And we end up with two output. And that's what we're done with. Okay? So we start off with output that looks just like the signal. We end up with, these are just the transform coefficients. So how do you get these coefficients? What are they? Probably the most famous wavelets are these Dubochet or Daub-4 wavelets. Okay, so Dubochet was a mathematician who derived in using some very simple arguments what these coefficients should be. And then she was actually able to solve for them analytically. And here is an example. So these are 4 Dubochet coefficients. If you take these coefficients and you reinvert the transform, these are the filter coefficients, you reinvert a simple transform to see what the corresponding wavelet looks like, you get this here. So this is a Daub-4 or Dubochet-4 wavelet. So this is the wavelet. It looks fractal-like, which these things are, but the important thing is it oscillates, it's localized, it has moments that vanish. So it's actually pretty simple, leads to good analysis. So that's all you need to have in your computer to do the analysis. So we're essentially done. Let's review what we've done in this latter part of the lecture in particular. We've taken the continuous wavelet transformation, which had all this interesting mathematics and physics in it, and we've developed an algorithm, just a tool, computer tool, so that we can evaluate those transforms discretely. Take a discrete number of points and be rapid. Okay? So that's the pyramid algorithm. So here is the transform we're trying to evaluate. It is signal times a wavelet integrated over all time. Since we have discrete measurements of time, we'll just evaluate the integral discretely as well at exactly the same places. So we replace the integral by a sum. The transform process, this integration here, is the equivalent to filtering. So then we just use the engineering technique of passing a signal through filter trees to get all of the transform coefficients out. Okay, very clever. And the multiple scales inherent in wavelets, we have to have different scales for different frequencies at different times. That's all handled just by the passing it through the filters, and then a filter and a whole tree of filters. So, good. The compression comes because when we end up with this, we only have n, the number of signals we've measured, points, and we have n components. No more components that we measured. That's the most you can determine independently. That's all we need. And we have further data compression by being able to throw away some of the details if you don't want a detailed picture. Okay? So this is the basis of the digital technology used in cameras, JPEG. Just this year, I know I'm dating myself, but just this year, the Nobel Prize in Physics went to a bunch of scientists, 2 of whom developed the CCDs, the charge-coupled devices, which is the basis of digital cameras, in part in recognition of how it's all changed the world, this digital technology being incorporated with computer technology and mixed together. This is, of course, the mathematics, which now you're one of the few who understand it, that have gone behind and permitted this great revolution. So we have some tools at our disposal. I think now we should get on and start looking at some physics problems with these tools, which we'll do. So I hope to see you again soon. Bye-bye.